Ever wonder how your phone, your computer, your entire office building, how all of it stays connected to the internet? It's not magic. It all starts with a blueprint, a fundamental design that dictates how everything talks to everything else. And today, we're diving deep into that blueprint, network topologies.
So let me just ask you this to get started. Imagine you're standing in a room with, say, a dozen computers. How would you actually connect them all so they can share info? Seriously, think about it. Would you link them up in one long chain? Maybe connect them all to some central box? Or go crazy and connect every single one directly to every other one? The way you answer that question, well, that's your network's topology.
So here's our game plan for today. We're going to start with what this network blueprint actually is. Then we'll get into why it matters so much. After that, the fun part, a tour of the most common designs. Then we'll check out some more advanced setups, and finally, we'll wrap up with how you actually pick the right one for the job.
Okay, let's dive right in. Section 1, the network blueprint. Before we go any further, we need to get on the same page about what a network topology actually is.
Simply put, a network topology is the layout of a network. The best way to think about it is like a city's road system. You've got your houses and buildings, those are your computers and devices, and you've got the roads connecting them, those are the cables. But it's not just about the physical streets, it's also about how the traffic, your data, is allowed to flow through them.
And that brings up a really crucial point. There's a big difference between the physical topology and the logical topology. The physical one is what you can actually see and touch, the wires, the routers, where everything is literally plugged in. But the logical topology, that's how the data thinks it's moving. It's the digital path the information takes, which might be totally different from the physical layout. It's like having a map of all the roads, but the traffic laws tell you which ones you're actually allowed to drive on.
Okay, so now we know what it is. Let's move on to why this blueprint matters so much. Because believe me, choosing the right design has huge real-world consequences for performance, for cost, and for how reliable your network is.
And the benefits of getting this right are incredibly practical. It's the difference between a network that's blazing fast and one that's painfully slow. When something inevitably breaks, a good topology makes it 100 times easier to find and fix the problem. This isn't just theory. It's about saving time, saving money, and saving yourself a massive headache down the line. All right, time for the main event. Let's take a tour of the different topologies out there. Think of this as a gallery of the classic designs, the foundational ideas that all modern networks are built on.
First up, we have the bus topology. This is the simplest of them all. Picture one long hallway in a building. That's the central cable, or bus. Every single office or computer connects directly to that one hallway. All the communication has to travel up and down that single backbone.
Now, the beauty of the bus is that it's super simple and cheap to set up. That's why it was pretty popular for small early networks. But, and this is a huge but, it has one massive critical flaw. If that main cable, that single hallway, gets damaged or fails, the entire network is dead. Kaput! It's a single point of failure that makes it way too risky for most modern uses.
Next, we have the star topology, and I can almost guarantee this is the one you're most familiar with. Think of a cul-de-sac in a suburban neighborhood. Every house has its own driveway connecting to that central point. In a network, every computer connects to a central device, like a switch or a hub. This is the design in your home, your school, your office. It's everywhere.
And you can see why it's so popular, right? If the cable to my computer goes bad, it doesn't affect anyone else on the network. Plus, adding a new computer is as simple as running a new cable to the center. The only real weakness is that central device. If the hub fails, then yeah, the whole network stops. But that's a much more manageable risk. Now for something a little different, the ring topology. Just like the name says, all the devices are connected in a circle, like a ring. Each computer is connected directly to two neighbors, one on each side, which forms this continuous loop for data to travel around.
The big advantage here is fairness. Since the data goes around in a circle, every device gets an equal shot to send information. But a lot like the bus, it can suffer from a single point of failure. If just one computer in that ring goes down, it can break the entire circle and disrupt communication for everybody. You used to see this design a lot in older telecom networks.
So we've seen the classic three, but what happens when you need more? Let's move into some more advanced designs, the ones built for situations that demand some serious power, scale, and reliability.
And this brings us to the mesh topology, the absolute champion of reliability. The best analogy is a flight map, where every single city has a direct flight to every other city. That's a mesh network. Every single device is connected directly to every other device, creating this incredible web of redundant paths. The advantage here is just insane reliability. If one connection fails, who cares? The data just instantly finds another way to get there. There is no single point of failure. The downside? As you can imagine, it is incredibly expensive and complicated to set up because of all the wiring involved. That's why you see this in mission-critical systems, like in the military or for scientific research where failure is just not an option.
Of course, in the real world, you don't always have to pick just one design. You can mix and match. A tree topology, for example, connects a bunch of star networks together along a main bus backbone. It's perfect for a big university campus. And a hybrid topology is exactly what it sounds like. You take two or more of these designs and combine them to get the best of all worlds.
Okay, final section. We've seen all the building blocks, so how does a network architect actually put it all together and decide which blueprint to use for the job?
Well, it's all about trade-offs. You're constantly balancing cost against reliability and scale. In the past, if you needed something cheap and simple, a bus might have worked. For a modern office or school, the star is the clear winner for its balance of cost and reliability. And if you need a network that absolutely positively cannot fail, you pony up the cash for a mesh network. It's all about picking the right tool for the job.
And this is where it gets really cool in the real world. Let's imagine a huge company. They'll probably use a star topology inside each department because it's easy to manage day to day. Then they might connect all the different office branches across a city using a tree structure. But for the absolutely critical link between their main headquarters and their backup data center, you better believe they're going to use a super reliable mesh topology for that. The end result is a powerful, flexible, hybrid network perfectly tailored to their needs.
So you see, network design is all about making smart choices and balancing trade-offs. The next time you connect to your home Wi-Fi, you can nod and say, "Ah, yes, my little star topology." But it makes you think, right? As our world gets more and more connected, with smart cities, self-driving cars, the whole Internet of Things, the networks of the future will have to be even more powerful and resilient. What will they look like? Will we see giant, city-spanning mesh networks? It's a pretty exciting question to think about. Thanks for joining me.